Okay, so welcome back. I want to start with a personal anecdote that has nothing to do with landslide and mass wasting. I was going up in the elevator this morning at work, and my fellow rider pushed the wrong button and said, "Oh, I'm sorry, because now we're going to be momentarily delayed." And then the elevator opened, and this woman got on right then, and she said, "Oh, yay, the elevator came." And I said, "Oh, that was an accident." She said, "There's no such thing as an accident." And I thought that was profound because we're talking about landslides today, and there's no such thing as an accident with regards to landslides. You'll read in your book this week about some horrible landslides that are just awful, and they were preventable, and they had to do with coal mining. So there were coal tips, so piles of spoiled rock that are associated with coal mining that were piled up in Aberfan, Wales, which is a coal mining really country. And so it is a mass wasting event. It was considered a landslide, and we'll talk about the definition of a landslide. So it was a natural disaster, but it happened as a result of us doing things wrong. Philippines, you build on really steep slopes. You'll hear about the Lady landslide in the book as well. Also, a situation where, maybe we shouldn't have built there. Turtle Mountain, Alberta, Canada, the Frank Rockslide. I'll show you a picture of Turtle Mountain. It's so called because it looks like a turtle. But there was a terrible landslide, and about half the town was buried. And they were coal mining in the base of the mountain. So this is a type of natural disaster that, yes, is actually natural. And the first thing I'll do is define what it is. It's movement down slope because of gravity. So these things are because of gravity, but they are preventable in some ways. We'll talk about how we prevent them. And they are also things that we know where and when they're going to happen. I don't talk a lot about avalanches, but avalanches are a form of mass wasting. We know when they're going to happen, and we shouldn't be building on slopes. So that was just, I don't know, that resonated with me. This woman got on with her big arty earrings and said there's no such thing as an accident. And I think that really holds true here. I sent you already the weekly recap, but it was, I guess, a pre-cap, you can call it. And there's a link to recent landslides, and they happen all over the world, all the time. So I'll tell you, I don't want to overwhelm you with statistics, but in looking at them, I looked at it a couple days ago. Apologies, I didn't look at it the last couple days. On the 20th of October, Oman, a mountain collapsed. The 19th of October, Philippines, 87 families were evacuated. Vietnam on the 12th, this is all October, 40 people were killed, 22 are still missing. The 1st of October, China, there were 23 killed, and 2.8 million people were affected. Then in early or late September, Yosemite, there was a rockfall. One person was dead, one person injured. Turkey, the 28th, 4 people died because of flash floods and landslides. Uganda, the 27th of September, 10 dead, 12 missing. Tibet, September 14th, that's because of melting permafrost linked to climate change, probably. Italy, on September 10th, 6 dead, 2 missing. Pradesh, India, there on the 12th of September, there was a massive landslide, buried a bunch of cars and a temple. So I could go on about this, but that link is interesting because it shows this isn't really something that happens in restricted areas. It just happens anywhere there's a slope. So I'd encourage you to look at that and to see what's gone on with regards to landslides. So without further ado, let's look at landslides. I like to open up, so the others, I just talked about the others, with talking about La Conchita, California. And with California in general, as Bonnie made reference to, it is said that California, I've said this before, has 4 seasons: earthquake, flood, landslides, and fire. We talked about fire last week. We talked about how that's a chaparral. It's a fire-dependent ecosystem. It's supposed to burn, right? There are earthquakes. We talked about California there. There are also a lot of landslides. So geologically, sorry, I'm in this little box in the corner. I like to pantomime things. So there, California it was underwater of the sea level for a long time. So sediment was piling up, piling up, piling up. And then earthquakes and tectonics lifted up my hands look enormous when I put them up there. So, the bedrock was lifted up. There's this pile of sediment on top of it here. It's soft, it's unconsolidated. Maybe you can see that from this rock cut here, right? Then you have these floods. Water saturates these slopes, and we'll see what role water plays in landslides. We cut into these sediments, these piles of uplifted sediment, as you can see here, for roads. We cut into them to build buildings, and the wildfires burn. Maybe you saw that storm chaser video from last week. The wildfires just burn, and they burn up slopes when you remove vegetation. As we will see, there is a removal of the anchor of these really precariously perched sediments. When there's an earthquake, you shake it, you change its stability. So we have a lot going on in California that make for landslides. This is not the most recent example of a landslide, but this picture is, I think, an interesting thing to look at. In 1995, there was a landslide here, and it happened, this will make sense to you in a minute, because we oversteepened the angle of Repose. This road oversteepened, and you have a landslide. We'll talk about the type of landslide that's there. Covered 9 houses initially, and then later another slip on that same day covered 5 houses, 1.3 million cubic meters of material that just came down. And then interesting, almost to the day, 10 years later, 2005, there was a bigger slide in this same area, La Conchita. 10 people died. There were 13 houses that were just totally destroyed and 23 that were badly damaged. So got to build somewhere, right? But if you watch the Storm Chaser video on wildfires from last week, you see that California is, not the best place to burn. I think it was George who said last week about, I think George or Jacob, about the Yellowstone fire in the late 90s, that there was a raging debate about, no pun intended, controlled burns. So, what do you do with regards to controlled burns in these regions? You can prevent bigger fires if you cause littler fires, but there's houses where you would cause the fires. Same thing with landslides. We actually do controlled landslides by shooting the slopes and doing other things. But where you already have a house there, kind of what do you do? So, California. So what is mass wasting? Mass wasting is a catch-all geologic term for things that perhaps of as landslides. The definition here is that, and there's some technical terms here. It's super simple stuff. Not to trivialize the technical nature of it. Engineering stuff is just so simple. So cookie cutter. Anyway, it's the gravitational movement of material down a hill or mountain. This is different from weathering and erosion, which we talked about the second day of classes, or the first day when we talked about sedimentary rocks, right? We talked about how weathering, rain and wind, breaks apart rocks, and then water or wind transports them from their source area to their end area. That's not what's happening here. The only thing, and I try to trick students all the time with this in the day school, what causes a landslide? What causes a rockfall? What causes mass wasting? The only force here is gravity. That's all that you're looking at. And that may be confusing a little bit, because the thing is, sometimes when you look at things like debris flows, mudslides, the events are characterized and classified in part based on how much water is there. So how can you say, that it's only gravity? Water's there, and sometimes it's there even more than the sediments that are present, but you could see passive agent. It's just sitting there with the sediment. It's sitting there in the interstitial spaces. It's sitting there in between the grains of sediment, and the whole thing gets pulled down simply by gravity. So that's all it is. I've written this twice here, right? If you're taking notes, underline it, highlight it, do whatever you need to do to understand the only thing that's happening here, so why I say that it's so simple, is gravity is pulling material downslope. That's it. And we'll talk about different types. You can see flow, slide, subsidence. We'll look at those later. Sue, I think was it, that was asking about, forgive me, I get a lot of emails about sinkholes. So we'll talk a little bit about sinkholes at the end of class. But, right, that's it, gravity, that's it. That said, there are some factors that make it more likely to have a landslide, and that includes, I should probably have written sudden, the sudden presence of water. Where water wasn't, the slope attains a stability. Then you add water later, we'll see what that does. Leave it at that. Geology. You can imagine, right, that if you have, this is why we talked about rocks and sediments and minerals. Do you have structurally sound crystalline granite or schist or nice, right, metamorphic or sedimentary rocks that are super strong and make good building materials? You can have a vertical face or even a negative face, right, an overhang, and it stays in the face of gravity. But if you have a pile of sand, which is essentially what California is, that's not a good type of geology to withstand the constant pull of gravity. And then the steepness of slope. Just like with rivers and flooding, the steeper something is, the more likely you are to have gravity pull something down. And we will look at why. Why? Well, because slopes, it kills me to be in a little box here. I like to use my keys, and I like to lift up tables, and sorry, I'll stop complaining. So slopes are at war. There's two forces acting on a slope. One is called shear stress, and that is a downward pull, and it is what causes the disasters, essentially. And then shear strength, which is what keeps stuff on the slope, keeps things stable, and that's what holds things together. And that's a function of sort of interior or internal friction of the material. So what do you mean by this? I thought you said gravity is the only force. Now you're saying there's two forces. Ha ha. This is nothing more than gravity being subdivided into two sort of subcomponents. So I'll show you that in a minute. But all slopes are at war. There's a force constantly trying to pull things down, and there's a force constantly trying to keep things on. The end result, oh, wait, why did I put that there? Yeah, all right, I'll do this, okay. We'll talk about the end result in a minute. Sorry, swap slides. Threw myself off. Okay, here's basic physics. Again, if you're not mathematically inclined, don't worry. I'm going to go to this so I can be bigger. Now I'm big. All right, so here is a flat slope, so zero slope. I put my keys, need something bigger, onto this slope. You see the keys, right? So are they going to go anywhere? No, Amelia, sorry, that's old. Are they going to go anywhere, these keys, if I keep this perfectly flat? No, yeah, no, right? No, why? Why aren't they going to go anywhere? Yeah, right? Gravity is pulling them straight into the center of Earth. Exactly, everybody's saying that. Excellent, right? Now what happens if I start to tip it? For a while, the keys stay on there, but at some point, the angle becomes too much, and the keys slide off, right? Good. That's a little example. So let's go back to the other sharing. So that's what you're looking at in this picture. That is simply introphysics. My little arrow. Here is the notebook that I had. Here are the keys. And if it's totally flat, here's gravity right here. Gravity is pulling straight down. So you can imagine that if the table was totally flat, the keys are right here. Gravity is pulling the keys straight down because of electrons can't go through the notebook, so it stays there. Now I started to tip the notebook, right? When you tip the notebook, you subdivide gravity. Those of you who have taken physics, no problem. If you didn't, you have these vectors here, right? Force and direction. Gravity gets subdivided into normal force, F sub n, which is shear strength. Part of gravity is pulling down on this block or keys and keeping it on the table, on the notebook, despite there being a slope. But gravity, again, being subdivided, the other part of it is the downslope force. Written here is F sub d. It's just the downslope force. This is shear stress. It's a function of the weight of the material and the steepness of the slope. And that's what's pulling the keys off the notebook. So in this situation, this first one, what you have is that the normal force, because the length of these errors is proportional to the amount of force, shear stress is less than shear strength, right? There's shear strength, here's shear stress. But then I made the notebook even steeper, and you see what happened. Now the normal force that's perpendicular to the slope is less than the downslope force, and so this one wins. So shear stress here written as F sub n, no, sorry, F sub d, downslope, and shear strength, F sub n, are fighting it out, and whenever the downslope force becomes greater than the normal force, you have a mass wasting event. So again, the slopes are at war. The end result here is that you have something called the angle of repose. Sounds like a yoga pose, right? It's simply the angle that grains can be piled to without falling over. And all the different materials have different angles of repose. So you can see here that, where's my little arrow? Angular pebbles, they have a 45-degree angle of repose. What that means is that you can pile them 45 degrees relative to horizontal before shear stress wins out over shear strength. Up here, coarse sand, 40 degrees, no matter where you go, all over Earth, whether it is Australia, whether it is Boston. Coarse sand, if you take it in a bucket and you dump it out, it's going to attain a 40-degree angle of repose. Fine sand, 35 degrees. So each material has their specific engineering property, which is their angle of repose, which is simply the maximum angle that it can be piled without having shear stress, or F sub d, the downslope force, win out. So most of the time, slopes have come to this truth where the shear strength is winning, sometimes winning ever so slightly, which is the point of your lab, and the slope will be stable. But conditions on Earth frequently change, as we know from looking at plate tectonics, from looking at weathering, right? It's always the fact that water, wind, earthquakes, that sort of thing. So the angle of repose, that stable angle, can change when you saturate the material with water. We'll talk about that in a minute. When you shake Earth, think about a sandbox. If you have a sandbox up here and you start shaking the sand, you've piled the sand to an angle of repose, you start shaking it, the sand will come down to a flat area. It's the same thing with earthquakes. You shake a slope and this angle of repose gets less. Regolith, I introduced this term because you'll see it in the lab, expansion and contraction of regolith. So seasonally or daily, so if you're in the desert, for example, In the daytime, the sun's beating down on the rocks and the molecules are vibrating like crazy and the whole rock mass expands. And then at night, the sun goes away. There's no water to hold the heat of the sun from the day, so it gets really cold at night. And so the molecules vibrate a lot less rapidly, becomes more dense, and material kind of shrinks. You can imagine that, again, a daily or seasonal expansion and contraction of rocks is not good for the material property of the rocks. So you can start making cracks. The cracks can get bigger. There can be more and more cracks. So what was once stable when it first was exposed to the surface, after years and years of it will suddenly be less stable and gravity will be able to pull it down. And then undercutting, I'll show you a couple of pictures of undercutting next, by us. That doesn't mean the United States, it means humans, La Conchita. Undercutting of slopes. This happens naturally after flooding. It happens naturally at the coast because of the energy that waves have. And we are very good at being our own worst enemies on slopes by undercutting. There's some simple, throughout this, I have just really simple cartoon diagrams. I want you to be at ease about this. It's really simple stuff. You have new terms that I think can be daunting, and the lab is engineering based. It's what engineers do. It's actually what you do as an environmental engineer. But it's simply plug and chug equations. There's nothing difficult. Don't have to calculate cosines. You just have to change cells in an Excel spreadsheet and see how that factors in as you go through the equation. So here's a river. Pre-flood is the dashed line. So here's the river before the flood. And remember, we said that the faster rivers flow, the more energy they have, the more sediment they can erode and carry. So all the sediment got eroded. And post-flood, you have a steeper slope. This was the angle of repose. This material that composes the riverbed is probably, fine sand, and so it is only able to attain this angle. You've oversteepened it in flooding, so in the days after flood, this stuff will plop back down, and you will achieve the same angle on both sides, and it'll be a little lower because erosion has taken some sediment away, but that's it. So that's undercutting by rivers. Here's a different type of rock. So this is probably granite, the lighter colored stuff with some basalt that's gone in. It's all igneous stuff. And you see that in the first picture here, because this is such structurally sound material, the waves have been crashing here and cutting away, cutting away, cutting away. And you have this overhang, right? And so that part is erosion. And this is able to attain such a negative slope, essentially an overhang, because there's a tremendous amount of internal friction here. These molecules are being held together super strongly by covalent bonds. They're just, it's crystals. But up here, weathering is happening. And what happens, remember we said that water, we have all these connections now, right? Water is a substance that anomalously gets less dense when it freezes. So when it rains or there's any runoff, water gets into these cracks, and then at night, if it freezes, it hydraulically essentially jacks them open, and so now more water can go in, which cracks it open even more, and you're creating an unstable situation where eventually you have a type of landslide we'll talk about called rockfall. Does this, those of you who are local, does this look like any structure a little north of here that that fell away not too long ago? Some people who are here. Multiple attendees. Who gets it first? Who gets it first? Yes, excellent. Yep, the Old Man in the Mountain. 2003. Here's my file on landslides. The Boston Sunday Globe. New Hampshire says farewell to Old Man. I was going to scan this in, but I thought it was more quaint that I hold it up, this yellowed thing. There's the Old Man in the Mountain before and after. So sad. What are people from New Hampshire going to do? It's their road signs, it's their quarters, it's everything. It's their cultural identity. So what happened in 2003 quietly just fell. And it fell because there was, same thing here, there was some cracks at the top, and eventually gravity pulled it down. There wasn't any wind, any water pulling it, just gravity pulled it down quietly. Nobody died. It was just discovered that the poor old man in the mountain had perished. It's interesting to talk to people from New Hampshire about this. They're so reluctant to let their personal identity go that they're talking about either projecting a hologram up onto that area. Was this there a couple, 3-4 weeks ago? Yeah. Or they're going to epoxy something there and reconstruct him. They're not letting this man go. So yeah, I get it, right? Look at the New Hampshire quarter. That's their thing. So there's rivers and oceans and other things undercutting. Again, simple diagrams, so you see how simple this stuff is. Here's a bad situation. This is what happens in California. An unscrupulous developer. We talked, those of us who are here at 5, talked about unscrupulous developers, the devils. There is a situation where this material can attain only this angle of repose. That's it, right? But here goes some developer, this happens all the time in California, who cut this, took the fill, now someone can pull this out, it's called fill, piled it up over here, built 2 little McMansions, sold their houses, and got the heck out of there, because what's going to happen to the blue house? Yep, exactly. This stuff's going to come right on top of it. What's going to happen to the brown house? Yeah, Hamza, right, landslide. So this one will be buried because this stuff is going to go back and attain this angle. What's going to happen here? Both gone, yeah. So this one will stay here, but be buried because we want this angle. So this angle is going to fail and come to this angle. And then this is too steep, so this whole thing is going to go, sorry to give you, yeah, exactly, Hamza, right, till you have the angle of repose. And it will just kind of go back to what this was. So not a good idea to undercut, but we do it all the time, everywhere. We'll talk about how we can try to make that at least temporarily stable. And yeah, the developer hopes that he or she sells those houses before any sort of failure happens in the, we'll talk about retaining walls. So another example from California, here's Half Moon Bay. This is a beautiful area. You see these oversteepened cliffs because of the waves. And then here, there's a couple of pictures. This is a small town about 20 minutes south of San Francisco. The angle, sorry, I keep using my wrong pointer. The angle of repose goes something like this. It continues up behind this car, but we've cut into this. This amazes me if you've ever driven around in California. They've got just little Jersey barriers here. This mighty pile of sediment is waiting to fall. Holy cow. There's another picture of it. So the angle of repose, these are actually sent to me by a student who lives there, would come, sort of come like this and continue on over here. But we've oversteepened this. And yeah, nothing stopping the stuff from falling. Yeah, landslide, yeah. So, yeah, this is oversteepening. This is what happened in the rain. Let's see. All right, okay. All right, okay. So we shouldn't oversteepen things. So let's talk about water for a minute. The way I like to talk about water is to pretend that we're all at the beach. We have met there for end of the semester party. Yes, we can, even though it's November, because I was just on the beach a couple of hours ago, and it is, yeah, what was it, 79 degrees. So we decided we're going to build a sandcastle. And yes, Colorado, yes, it happens everywhere. So we go to the beach, we jump out onto the boardwalk, and in the summer when it's really hot, this is the area that there's no algae that's washed up. It's burning, searing hot sand. We take our little red plastic pail, we scoop up some sand, and we dump it, and we maybe pat it down with our blue plastic shovel, and we dump it over, and we lift it up. What do we have? What does that look like? Our sandcastle that we just built in the very back beach where there's no water. Yeah, exactly. It falls apart, as Katie said. It will attain about 30-degree angle of repose if you have fine sand on the beach, right? That's it. There's nothing we can do really to make a beautiful sandcastle. So where do we go if we want to make a beautiful sandcastle with our red plastic pail? Yeah, exactly. To the water. Yeah, everybody's saying that. Excellent. We walk towards the water. We go to the place where, the tide is going out. It's recently wet. We scoop up that sand. We pack it down with our shovel. We flip it over. We lift it up. And then we have the exact imprint of the bucket. We can build turrets. We can dig into it. We make little moats, right? This is because of some of the properties of water, right? The top 10 coolest things about water. I love when we can get to start making these connections. Water is sticky, and it sticks to itself, and it sticks to other things. It holds things together. So the best place to make a sandcastle, everyone already knows, right, is in the beach where the sand is wet. You can do all kinds of amazing things. We can sit there all day making all sorts of things. What if then we'd subscribe to the school of thought that more is better? And we say, oh, this water's awesome, so let's go to the surf zone. We take our bucket and we scoop up a slurry that's about half water, half sediment. Yeah, we have a lot of water in here. We turn it over and we lift it up. What does that sandcastle look like? Mush, yeah, right. It flows. It behaves like a liquid, exactly. As Katie said, it flows. So what does water do to slopes? The question can only be answered by asking how much. If you have some water, but the grains are all touching each other, you have this pore water pressure that's there that holds everything together. You have a cohesiveness, which is just a stickiness, the ability to stay together. The lab talks about cohesion. This is simply how sticky the material is, how able it is to stick together. Too much is bad. When you get to a point where there's so much water that the grains are no longer touching, they get jacked apart. It will behave as we saw with, if you watch that Japan documentary on tsunami, it will liquefy, liquefaction. It behaves like a liquid. It's also the case that yeah, the back beach, right? You have too little water, not good. Too much water, not good. So water is good for slopes as long as you have the right amount. So that's water. Yeah, went twice. The same thing with vegetation. In general, vegetation is great for slopes. You can attain a much higher angle of repose if you plant the slope with vegetation. If you have trees, if you have shrubs, if you have grass, anything that can anchor the slopes. Remember, we talked about meandering rivers weren't able to exist before vegetation. So vegetation is great for slopes because you can anchor it. The roots come together, bind everything together, and you have a great cohesion. It is the case, though, so if you take trees away from a steep slope, you're going to lower the angle of repose. As you see in this next picture, there's a forest here. And this forest, the trees and the grass and the shrubs all have this root zone that makes for an angle of repose that's much steeper than the material properties of this sediment can hold. So someone has come in and cut down all the trees. Now what's happening is these aren't the root balls that are being excised. It is a type of mass wasting. We'll call those slump. We'll look at that in a minute. This is going to eventually fail to the point where you're going to have an angle of repose that goes something like that, much less. So removing trees is bad. But I'm going to back up onto the previous slide because the other thing that can happen is engineers who do hill slope analyses and who plant vegetation as a method of preventing mass wasting events have to be really careful about what type of vegetation they choose. Because if they put in hydrophilic vegetation that loves water, it'll suck too much out, and that will be, the analogy would be going from the beach where the sand is wet back to where the sand is dry. So if you have the wrong kind of vegetation and it sucks all the water out, then you lower the cohesion. So in general, vegetation is good, but you have to make sure you have the right type of vegetation or you end up with problems. So we will go on and look at some types of mass wasting. This is kind of a summary slide. We'll talk about all these. I'm not going to mention lahars again. Remember we talked about lahars when we talked about volcanoes. Lahar is the pyroclastic debris, the ash that mixes with water if it's raining, or water in a river, or melting snow at the top of the volcano, and it becomes this dense mud-like material that flows down the slope. That initial process of a lahar is a volcanic process, but as we said, these things can be re-wet for decades every time it rains. What happens is, so look at that, the longest block diagram there. Yes, some of the water will erode away the lahar, but some of it will infiltrate. See all these connections? We're talking about all these other classes. Yay. Love this part of the semester. The water will infiltrate and it will make the sediment, the pyroclastic debris, heavier, and gravity will pull it down. So there's a component of erosion that happens when it first rains, but later that is heavier and it goes down. So that's a lahar. But let's look at some of these types. The first type of mass wasting, not a landslide. I'll tell you later, essentially, that a landslide is anything you can see, some perceptible movement of material downslope. Creep, you can't see it. So what happens is you're standing at the base of the slope. Your life is not in danger, but you see evidence here, if you look at it, that there's downslope movement, right? So here's this outcrop, but you see this type of rock has gone down to here. Same thing with this. I don't know if this is coal or what, but it's gone down here. This one too, right? So creep is a very slow, the definition, it's a very slow downslope movement of material, of soil and loose fragments. This is the way that it looks if you blew up this, not exploded, but expanded on this hill slope. What you see is that here's the original position. We'll follow this darker colored piece of rock. When this hill slope freezes, for example, but you could use any temperature extreme. You could also say, like in the desert in the daytime, thermal expansion because of it getting a lot hotter. The whole slope moves up perpendicular to the slope. But then, because of gravity, when the frost melts or when the really hot rocks cool, it will go straight down to the center of Earth because of gravity. It goes up at an angle, straight down. It's kind of like longshore drift, if anyone knows about physical oceanography and coastal processes. Up at an angle, straight down. So this is what happens, right? Straight down, but up at an angle. So the net movement is that over the days, over the seasons, over the years, stuff slowly goes down slope. So this isn't horrible in and of itself, right? Because you can't even see it happening. So it's not like you're going to die from creep. However, eventually what can happen is, I think here there was a retaining wall. So we'll talk about how to prevent this. It might have been a retaining wall here. And the sediment, the vegetation wasn't growing as well as it should have. And you've oversteepened this angle, so you had creep eventually cause a slump, which is another type of mass wasting event. You can see creep sort of anecdotally. We don't install fence posts at a 45-degree angle to the slope. So what's happened here again is this slope has had straight out, down, straight out, down. And the fence posts that are stuck into it are now tipped. So that's the result of creep. Here is another picture of creep. You have the road coming by and the posts for the electric lines are tilted. This is not necessarily an unsafe situation because they're all tilted in the same direction. So you see the power lines aren't overstretched. Here you have curved tree trunks. I think I have another picture of this later when we talk about solar flexion. So the tree wants to grow straight up. Creep is bringing the trunk down so it curves through time. Gravestones can tilt. So that is creep. Here's a picture of trees growing in creeping soil. So you could be walking along in a path or coming through the woods here, and your life is not in danger, but you're essentially in a mass wasting environment. And these trees are all curved because the stuff is slowly moving down slope, but the tree, because of the leaves, grows straight up towards the sun. So that's creep, not very terrible. Solar flexion is a specialized case of creep. Sorry, when I load these slides, the text moves. I wouldn't have designed a slide that looks like that with an N on the bottom. Solar flexion is creep in permafrost. So permafrost is permanently frozen ground, except for in the summer, the active layer, the upper couple of centimeters, will thaw. The same thing happens on a slope. It will thaw and mush down. I like that word. And then it will freeze again and go straight up and then mush down. And so you can see it looks like waves on the hill slope, but it's a creeping slope. There's some solar flexion in Alaska. So again, it looks like water shaped to this process, right? Because it's going this up, down, up, down. So another type of mass wasting event is called a debris flow. And a debris flow is moderately fast, moderately wet. These types of mass wasting events are categorized in those two ways: the speed with which they occur and the amount of water that's present. Remember, the water is just a passive agent, but it's there. So in a debris flow, probably what happened in this region is that water, there was a big rainfall event. Yes, there might have been some erosion. Water saturated that part of the slope here that is soil, right? And so it got too heavy. So this angle of repose that was fine when the material was dry got too heavy, and you have a debris flow. So it's moderately fast. There's a result of a debris flow. Again, we have coastal California. You can see that it's also, there's a lot of water that has shaped this process. Idaho, some debris flow. Materials over here. It kind of came out this way and then went that way. Slump. This is another type of mass wasting that's moderately fast. And the interesting thing here is that it's this movement down slope along a curved rupture surface. So what's happened here is that you have a, oops, there. Gosh. No, I just want something to be that. Oh. It's like I don't have opposable thumbs. So, Amelia, if you can hear this, can you help me? That over a little more, but not too much. Oh, God. Anyway. Let me take at least my arrow and come over here. So this has been oversteepened, cut away by someone. Yeah, exactly how you sit in your chair, slumped down, right? It's bad for your back. So because of this oversteepened angle, you had this first slump happen. You have a curved rupture surface here. And this is called a scarp, this face that's vertical. And so what that did was to oversteepen this one. So you have another slump and another slump and another slump. This calls to mind the recent Norway landslide. Fascinating situation where draw whiteboard. Okay. Draw Jeopardy style. So here's some mountains, and then here's a big plain. And then it went into a lake. And a farmer, Sounds like the setup for a joke, right? Has a little house here. He's in Norway. And he decided to build a barn. And so he excavated a basement for his barn. So he cut this all away. Didn't know what to do with the sediment. So he piled it right here next to the be blue. It's not next to the lake. But you see what he did. There was the angle of repose. Ooh, I don't want to be drawing. I just want the arrow. Here was the angle of, angle of repose. Anyway, he oversteepened it. So it caused a slump that went like this. That all went into the ocean. Took away his own house. So they occur successively. Carried away a bunch of the town. And there's actually black and white video footage of a church that's just kind of floating on the lake. And he destroyed about a third of the town because he innocently piled this pile of sediment next to the lake. So fascinating, the Risa Norway slide. Share my screen. Okay. No, I don't. Two. So slump can be small and fairly innocuous. You see this next to the road. Yeah, exactly. Yeah, he was popular. Someone asked me if he got in trouble. I don't think he did. If you're looking at slump development, just like I showed you creep, what you can see here is that this initial, probably a little one right here that you can't even see that much anymore, and then is causing this one, which is causing this bigger one. And now you see that it's different from creep because the telephone poles or the electric poles are straight up, but where they straddle a slump, these are over tight, so these can snap. Over here, you can't see, sorry, these trees, I don't know why this didn't load perfectly right, have died because the scarp and the scar essentially between these two will be a preferential conduit for water. So water will just infiltrate along that scarp, so those trees can no longer get enough water. The building here hasn't tipped forward, but you see where it straddles the slump scarp, there's cracks. The road's cracked here. So those are some lines of evidence that show you that you're in a slump environment. Last two, Rockslide. Do I have Frank Rockslide here? No? Okay. Yeah, all right. That's a slide. I don't know why I wrote fall. So Rockslide is the second fastest, and what you can see is that because of gravity, right? This is probably a structurally sound rock. It has bedding planes in it, can attain a very steep angle of repose, but you have water here, you have a river, there's some rain that's probably falling. Acids from the roots are eating away at this, making it less and less stable, and eventually gravity pulls this stuff down. The bottom of these, you have something called the talus slope, where it's a pile of rubble. It's not, again, the product of weathering and erosion, it's the product of gravity pulling things down. The rock slide, there is a little bit of an angle to this, so the rocks, it's exactly what you say, they slide down the side of this. When you have an even steeper slope, a vertical slope, you have a rock fall, they free fall. Those are dangerous, especially when you're driving at the base of one. Here is a picture of the Frank Rockfall. I talked about this a little bit. I don't want to say too much about it because you have a whole case study this evening on it, or this week on it. It was in 1903, though, in the town of Frank. And there was coal mining in the base of the mountain. And the blast probably triggered it, although the legal findings were that, it was just a freeze-thaw cycle. It buried over 100 people. Yeah, all sorts of cool stories about it. There's superstitions. It's a cursed mountain, Indian legend. So you'll read about that. I won't sit and repeat that. But it's just repeating itself today. The town rebuilt, it's sitting there, and it's an accident waiting to happen. So it didn't really learn from it. There's millions of tons of material that's on this slope, right upslope from where people live. So rock falls, here's another one, can be really, really dangerous. It is the case that sometimes in California, you see these really steep slopes here, they close the roads and they shoot munitions at the slope when it looks like it's really about to fail. They cause the failure in a controlled sense, and then they can haul this away. So sometimes that happens, equivalent of like a controlled burn. Side note, you can have these landslides that happen underwater. You can have subaqueous slopes moving, and this is something that can cause tsunami. I don't know if anyone is a Stephen Jay Gould fan, but he's a scientist at Harvard who was there. He's since retired. He wrote a book called "It's a Wonderful Life," not like the Jimmy Stewart movie, but what happened was he found a whole bunch of organisms that we never would have known existed. They were there's sediment on the continental shelf, and there's all these organisms just with soft parts, no hard parts, living here. And then subaqueous slope failures rapidly brought them to very deep parts of the ocean where there was no decomposition. Their bodies were preserved in the sediment, and he spent a lot of time there. So this is what it looks like, these successive slumps really in the ocean, turbidity current. That's where the soft-bodied organisms were preserved, and that can also cause tsunami. So we're going to keep sort of using the word landslide and mass wasting interchangeably. Landslide is any type of mass wasting that is perceptible. So if you can actually see the downslope movement of material, then you would call that a landslide. But everything is lumped into the category of mass wasting. Landslides also can be multiple types of mass wasting events all at once. Look at this, amazing, right? People building these houses. So what happened in this picture? These houses are built on hill slope. Right here is where we're sort of focusing in. There was this resistant cap rock here. So this is crystalline, strong stuff. Beneath it is the softer, unconsolidated stuff. And some developer did a structural stability analysis and said, no, it's all right if we oversteepen right here because this stuff's real strong. And it is, and it did form a ledge, except there was a series of torrential downpours. The water infiltrated through the cap rock and essentially liquefied the stuff beneath this, and you withdrew the structural support of the cap rock, and all of these homes, because it's a slump, at least this part, they stayed entire. So this house right here used to be up here, and along the curved rupture surface, it just got brought down. So it's amazing, amazing that we build in these places, yet build we do. So landslides also can happen because of liquefaction. We've talked about liquefaction, we talked about tsunami, we talked about liquefaction, we talked about earthquakes. What happens is, so these are flat particles because this is clay. Clay is flat and platy rather than spherical like sand and silt. In the first picture, the left-hand side of the screen, you have these flat platy clay, 1/256 of a millimeter, so they're microscopic. As long as they're all touching each other, it's okay. It's when there's so much water that they get hydraulically jacked apart that the whole mass behaves like a liquid and just flows down. So liquefaction is a common thing that happens with landslides. So what can we do to prevent mass wasting? These things, I won't read them all if I have a slide on each one. This is one of the more preventable types of landslides, of natural disasters, at least when we're talking about sort of temporarily being able to prevent them. How do we do this? These ways. Let's go into them all. First of all, we established that vegetation makes slopes more stable. And so what's going on here is that at the top you have a slump. You have a slump here, right? Curved rupture surface. This area is unstable. This area is unstable now. This is oversteepen. This is too much stuff here. So what you can do is kind of regrade this, bulldoze this down, and then put in trees. And eventually you can see that their root systems will suture together the slump. So this stuff comes down into here, and you have now a stable slope. So where you have deforestation for many things all over the world, all over Philippines, everywhere, and you have these landslides to revegetate forests will lessen and ameliorate the landslides. This top picture here is, remember we showed this, the brown house and the blue house here. There's a way to do this and do it a little more safely. So remember, this is oversteepen. This is oversteepen here. So if you take out this stuff too and put it over here, what you've done is to remove the load where it's too much. You regrade so it's closer to the angle of repose. You take the stuff that you pulled out of here and you put it over here. Maybe I'll do it here. You put it over here so you're providing structural support where you need to, and you removed excess load where you needed to. So that's a good way to do it. Then you can still build your two houses here, and you have less of a chance of losing them to mass wasting. Economics, exactly everything. That's what I say about everything. Yeah, in environmental science, I say there's no such thing as environmental problems. There are only economic problems. So you could say this really not about all the natural disasters, but about where people choose to live, economics, right? So here's an interesting thing. So I did my PhD in Syracuse, New York, and the Finger Lakes. Is anyone familiar with the Finger Lakes? Anyone? Okay, good. Yeah. All right. Yeah, people are familiar. I'm sorry. I'm going to keep going and messing myself up by, I'm going to share my screen. For those who don't know, oh, you were in Rochester, right? For those who don't know, let's see. Let's do satellite images. So I'll just leave these all up. Oh, that's the Belhurst Castle. That's such a cool place. They have a spigot in the wall and it pours red wine. Anyway, there's a lot of wineries or vineyards here because the soil is great. Why is the soil great? Well, all these lakes, I don't know if you can see my little finger thing here. These lakes were all carved as fingers or tongues of the glaciers moved along. Am I sharing my screen? Can you guys see this? I'll come back to you. Did I share it? Yeah, okay, it's good. All right. So anyway, these lakes are actually excised down beneath the sea level. Glaciers came and carved them enormously deep. This is Lake Ontario here. So Syracuse would be over here somewhere. So anyway, these are fingers of glaciers that came in and then melted back and they became these lakes. Over here, there's what's known as a dry Finger Lake over here. Yeah, Tully, New York. Sorry. And so Tully, New York is a dry Finger Lake because it didn't, the little piece of the glacier that was there didn't excise things deeply enough to leave a big glacial lake. And so, stop sharing. So a bunch of people built houses in Tully, which is, again, this dry Finger Lake. Yeah, okay. So this is what we're kind of looking at. These would be the Finger Lakes here. Tully, that pretend there was no water here. So people building all their houses along here, they have a beautiful view. This is just a valley because it's dry. And there was a bunch of rain, raining. And the water table, which is normally way down here, came up really high. And unbeknownst to geologists and the people that built houses here, there was something called a glide horizon, which is simply a layer of clay. It's pretty obvious that clay would be found around a lake because lake is a really quiet water environment. So the only stuff that's there is silts and clays. So you deposited this layer of clay, and clay is fine to build on as long as it's dry. When you wet it, it's highly porous. So there's a lot of space between the grains, but it's not very permeable. The water doesn't flow very quickly through it as it would through sand, for example, because water's sticky with its positive and negative charges, and clay is also sticky with its positive and negative charges. So just water gets in there and builds up. And then eventually what happened in Tully, this dry Finger Lake, is that this whole slab just slid down the glide horizon and dumped down into the dry Finger Lake. It's 50 acres of land that slid down in there. Wasn't very populated, so nobody died. There were 3 houses that were gone and 4 were badly damaged. The interesting thing about it is that, so we learned about it and we went to visit it because, it's in a geology program. The people whose houses got damaged and who got destroyed all submitted to their insurance companies, and all their claims got denied. Any ideas why? It happened over the span of about 2 hours. Let me see. I have a Tully thing here in my email. Yeah, about 2 hours. Okay, no, it's not on this sheet. Yeah, 2 hours. So it just slid. Why did all their claims, all 7 of them, get denied? I like asking insurance questions. Yep, exactly, Jeff, absolutely. Did you Google that or did you know that? Excellent. So it wasn't a flood, right? It was a landslide. And the insurance companies all said to the homeowners, you don't have landslide insurance. They said, of course we don't have landslide insurance. We're in central New York. It's totally flat here. So it was a landslide. And so they didn't have landslide insurance. They fought in court and none of them got any money. So their homes were just destroyed and they got no compensation for it. Excellent, Jeff. I still want to know if you Googled that or if you knew that. I'm impressed. So what can you do about that? And what do they do now around the Finger Lakes, especially where their house is? And that slope's not that, guess. Okay. Yeah. Okay. So total random side note, I used to ask as extra credit in the day school, a couple found out about a new type of insurance, and it was meteoroid insurance. I'm going to tell you this now, and we're going to talk about meteorites in about 3 weeks, but I'll forget by then. And then, sure enough, this extraterrestrial material impacted their house, burned up. They submitted a claim. Wait, it was meteoroid insurance, yeah. And it got denied. And so I asked them why. Maybe you don't know this yet because you haven't we haven't talked about meteorites. But a meteoroid is what it's called before it strikes Earth. So they should have bought meteorite insurance. Yeah, some people get it. The ones that don't are so angry that I asked that as an extra credit question. It's extra credit, whatever. What can you do with these glide horizons and to keep them dry? You simply install groundwater wells and you make sure that they're on and being pumped. You dump the water into the lower area or to wastewater treatment plant if you want to be really expensive, excuse me, about things, or somewhere else. Because again, as long as this clay is dry, I know I'm not supposed to monitor the chat, Amelia. I'm going to read it after. I was asked by 3 people to not monitor or correspond with the chat. We should put this, Amelia, if there's any way you can copy and paste the chat, which I sort of have my eye on, and put it into the discussion. I set up a discussion for each topic. We can go read about it and expand, because I would love to have more interaction with people. But again, the number of people here, it would be very difficult to get through the material. So please, yeah, let's make things interactive down there. Perfect, yeah. Stick them up on the discussion board so everyone can see them. Another thing you can do to prevent landslides is to essentially cause them by terracing. What do I mean by cause them? Well, here we have another unstable slope here, right? The angle of repose is something like this. And this is too much, so that's going to fail. So what you do is to terrace, or essentially build these steps here, and you've created a vertical face, so obviously this is going to fail, right? It's a vertical face in sediment. But what you do is you've removed the overall load from that slope, and so you lower the chance that there's going to be a catastrophic landslide that destroys that house. And you provide a bench here to catch the landslides in a controlled way. You can come remove that if you want, or just leave it. And so terracing, again, removes the overall load from here, and then also provides a place for the stuff to fall in a smaller, controlled fashion. I don't love this picture. I'll tell you why. Rivers flood, right? We've said that that's what they do. We spent a week looking at rivers, and they flood, and when they flood, they can erode the stream beds. So what's happening in this top picture here is that this river is flooding, and it's cutting in here, and you're imperiling this house. This is oversteepened. That's going to not have a good situation. So up gradient here, you rerouted the river channel onto this floodplain over here, and then you bring it back around and continue it. So if you're essentially making the opposite of an oxbow lake, you bring the river over. You can reroute the river channel. The reason I don't like this is because it makes it look like some crackpot engineer took this stuff and used it to fill the old river channel. You never do that, because look what you did. You have an even steeper slope that's even closer to the house. That would never happen. So I might just be misreading this cartoon diagram, but that's why I don't like it. What you would do is take the fill from here and fill it in. So you have the old sediment that's still here, plus this, and you kind of try to angle it a little bit. And that would make this better. Sue, good question. How feasible is it? It depends on so many things. It depends on what the rock is. So if this is all granite, that would be unbelievably expensive, but you wouldn't do it if it's granite, because it probably wouldn't erode that way. It would take, depending on the size of the river, right? So it wouldn't be the Mississippi. A medium-sized river, not even something as big as the Charles, but something a little smaller. You could take a backhoe and dig a river channel in maybe 3 days, dump that stuff over, be done with it. So yeah, it's expensive. And you wouldn't do it for one little brown house, but you might do it if there's a whole bunch of people living in one section of a river. And remember how we talked about that the river bends migrate down gradient? So maybe they were in an okay place 200 years ago, but the bend has migrated down, and so now they're imperiled. So you can just kind of reshape it. And so yes, money, as Elisa said, right? Riprap. You do this in the coast. This is illegal in Massachusetts. Those of you who logged on earlier, we were talking about Wetland Protection Acts in Massachusetts. You're not allowed to stabilize the coast in Massachusetts. The rationale there is that coastlines are a dynamic environment, and when you prevent erosion in your house, you're actually starving your neighbor's beach or area of their sediment supply. There's a natural longshore drift. You can't do this, but in some places you can. You're welcome, Sue. So what's happening here in the top pictures, you have these waves crashing, 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 and obviously this is sort of semi-consolidated sediment because it's an overhang, but that's not a good situation if you have houses or a hotel or a road or something there. So you throw in blocks of cement or anything like that, and that's riprap. And what happens is now the waves are giving their energy to those blocks, and you can see the water that's adjacent to the shore is quiet water environment. There's no more energy in the waves, so you cut down on erosion. We have done this with tires. Anyone know about the tires off the coast of Florida? We have tried to use tires both for artificial reefs and to cut down on shoreline erosion. It also is attempting to solve the problem of too many tires all over the earth that we can't do. We can only do limited things to recycle. And sometimes this actually works. You have this big tire reef and it creates environment for smaller fish, larger fish, and you cut down, beg your pardon, on wave energy. But it was a disaster in Florida. Didn't work at all. These artificial reefs that are trying to cut down on shoreline erosion. I think the estimates are that there are between 2 and 4 million tires off the coast of Florida, and environmental people are trying to clean them up, go diving, try to get them up. They're battering the real reefs, and they're just sitting there not absorbing wave energy. So this works with mixed success. Retaining wall, you can either put it directly on the slope or you can put it some distance away. So what you see is, I don't know, maybe this is California, not to pick on California, but you have this road and the car is driving and the car is going to be subjected to, as you can see, a rock slide. But if you put a retaining wall there, then you catch the material. You can also put a retaining wall directly up on the slope, depending on what's going on there. And that retaining wall will prevent the car from being damaged and kind of thrown off the road. If you drive on the Mass Pike, those of you who are local, sometimes you see these things that look like big metal dinner plates on the side of the road where there's a rock cut. You would use bolts, which are kind of like big nails, only in specialized cases, such as this one, where this is probably granite or some type of crystalline rock that's overall tremendously structurally sound, but you have a weak plane here. So there's a bedding plane here, and the bolts will come in and suture this material together. Obviously, this wouldn't work. I don't want to say obviously, that kind of sounds condescending. This wouldn't work in sediment, right? You couldn't bolt sediment. But if you have this rock that's really crystalline, structurally sound, no problem at all, except for this possible failure plane, when you suture that together, then you have a much more stable situation. So you'd use this, just like you'd lower the water table only with clay, you would bolt only with crystalline rock. So an avalanche shed, these are all over Italy, these are all over Switzerland. An avalanche is a type of mass wasting. So you have snow piling up on a slope, and eventually something happens. It either gets oversteepened or it melts a little too much, and you have these avalanches, mass wasting, and they can be very damaging, obviously, to people and to structures and to cars on roads. I beg your pardon. So the snow here is now going over this steel, corrugated steel or whatever, avalanche shed that's kind of like a tunnel, and so the car can drive. It's really scary to be in these when there's an avalanche. You hear this loud, it's like a train roaring overhead, but the avalanche shed keeps you safe. The avalanche goes over the road and everything is okay. So Sue had asked about sinkholes, and there's a last type of mass wasting event that's called subsidence. And subsidence is a specialized case because it happened in completely flat areas. Giant hand. Completely flat areas. So you have the vertical sinking of land. And really there are two main types of subsidence, sinkholes, which we'll look at, which happen quickly and just collapse. Or you can have subsidence or sinking over a long period of time. So, yeah, I don't love this slide. I don't like way into this slide. Subsidence can happen really quickly. A small sinkhole can happen in a couple of minutes, or it can be very slow. Think of a city. Anyone think of a city that you... Oh, Venice. Okay. Venice, how do you drive down the street? Yeah, exactly. In a boat. Did they make a city? Yeah, right. Did they make a city saying, oh, I think we'll be innovative about making our city and we will make water instead of dirt roads? Answer is no, right? It's built in a wetland type of material. Yeah, they built it into this wetland, and the land has been sinking, and the water level has stayed where it is. So the land and the water level have traded places. So that kind of subsidence, gravity pulling and compacting sediments, it happens in the delta of New Orleans too, right? Can happen over hundreds of years. This stuff can be natural or man-made. It can happen naturally, but also it's common that subsidence happens associated with solution mining. So if you're pumping groundwater out of the ground, like the San Joaquin Valley, I think that's now at 25 feet of subsidence because they're pulling all the groundwater out, and the sediment that's remaining gets compacted and settles and goes down by quite a bit. What else can it happen? Yeah, oil and gas, same thing. Oil and gas, if you pump oil and gas out, the whole land can sink. So it can be natural or it can be man-made. It's driven by gravity, which is why it's categorized as mass wasting. I don't know why I said like mass wasting. It's a type of mass wasting, but it's not a function of shear stress, shear strength. It's just gravity pulling things down. So look at that a little bit. There's a sinkhole. So what do I have about cave? Yeah, so here's what happens in caves. This is limestone. This brick-like pattern is geologists denoting the limestone. Limestone is a good building material if you can keep it in basic conditions, but all natural water is slightly acidic. It's slightly acidic because it is rain falling through the atmosphere. The atmosphere has a bunch of carbon dioxide in it. Carbon dioxide dissolves, turns into the dissolved phase of carbon dioxide, which is carbonic acid. So it eats away limestone. I see Sam says, yeah, it's this big, I call it Swiss cheese. I like honeycomb better, right? Huge. Florida's just this big block of Swiss cheese, or as Sam says, honeycomb, of these caves because Florida's mostly limestone. And what happens is slowly the water that's weakly acid dissolves away caves. And when you get to a situation where the roof of the cave, it's being eaten away, it can no longer hold up this thin roof in the presence of gravity, collapses in different areas, and those are sinkholes. If you read the book, The Lovely Bones, right, it's based on the fact that back through time, Floridians put waste. They threw their trash into these. They would put hazardous waste into them, which was not, malicious. They just thought, oh, that's just a way. Turns out they are polluting their own groundwater supplies. But this book, The Lovely Bones, maybe you can surmise what was going into this sinkhole. This book. Anyway, sinkholes happen all over the place in Florida. We haven't fully mapped out these caves. People don't go caving in them because they're filled with seawater because Florida is pretty much at sea level. But where's my sinkhole that I printed out just for Sue? Florida sinkhole swallows barn. 2 horses die despite rescuers' efforts to save the second one. Sad. I don't know why I printed this out. Sanford, Florida, 50-foot wide, 30-foot deep sinkhole destroyed a barn, killing 2 horses despite rescuers' desperate efforts to save the second one. Bob Bonwit had returned home from his nursing job Thursday night and was walking to his barn to feed carrots to his horses when he discovered the sinkhole had engulfed the barn. I nearly stepped into it, Bonwit said. The whole world was wrong. The horses were at the bottom of the pit, which was filling rapidly with groundwater. By the time Seminole County Sheriff's officials Another fire rescue personnel had arrived. The older horse, Jack, 17, had drowned. The other horse, 13-year-old Magic, was perched atop the dead horse, barely keeping its nose above water. So sad. Rescue workers were able to place a harness around Magic's body early Friday morning and tried to lift him out of the hole, but his back legs were stuck in the mud and he eventually died. Bonwich House is close to the sinkhole, but authorities could not say if that structure was in danger. Sanford is 19 miles north of Orlando. I know, those poor horses. Sue, you're the one who asked for this. Sinkholes occur when sand beneath the surface erodes and falls into underlying limestone cavities, causing the surface to collapse. Several factors may contribute to the collapse, including drought, excessive water pumping, traffic, construction, or heavy rain. The geology of Florida makes it especially vulnerable to sinkholes, although they are also found in Texas, Alabama, Missouri, Kentucky, Tennessee, and Pennsylvania. So you can't, that's a great question, Sue, you can't map them. So you just have to live with them, right? I sent you a video of 2 sinkholes that appeared within hours right next to each other. So if you didn't read the recap, weekly recap, which is a precap, you can see some video of that because I didn't want to spend a huge amount of time on subsident. But so caves and sinkholes are a type of this, and you can't map it. Oh, do I have that last picture? Let me see if that last picture came out. Darn it, I didn't leave it in here. Anyway, there was a picture of 2 houses, one fine and one collapsed by a sinkhole, and there's a realtor sign that says location, 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 not on a sinkhole. So, okay, so we finished with this one. So what happens, here's another sinkhole, is that, again, groundwater, which is weakly acidic, all natural waters are, yeah, right, that, Richard, that was the, okay, there were 2. So the video shows a bunch of Corvettes. The Winter Park sinkhole, which I sometimes talk about, it happened over a couple of hours, Winter Park, Florida, and there was a Porsche dealership that got swallowed up. So I think 14 Porsches went right in there, and a mobile home in a trailer park. A couple of them got swallowed up by the Winter Park sinkhole. So, yeah, I guess it turns out that many states have their problems, right, with regards to natural disasters, except for we in Massachusetts, we get nothing so far. Maybe an earthquake, but yeah. So yeah, it's amazing. So groundwater can dissolve away the cave until the roof essentially collapses onto itself, or when groundwater withdrawal or oil and gas withdrawal that we humans do, the ground can settle and compact. And so when you dissolve it, you make caves, it can collapse, and then you can sink the whole land over a large area. We talk about that in agricultural courses. I know. So they have there's this little, speaking of New York, let me see if I can do it here. Let's see, turn this way so I can, New York is shaped like this, and there's this little L shape of, I'm sure that didn't help because I'm 2-dimensional right now. This L shape of limestone, and so there's Howe Caverns, there is secret caves. You can go into these caves, really cool. I take my groundwater geochemistry students there so we can go caving, and we talk about dissolution, and we go to Saratoga Springs and we look at all the crazy different types of groundwater that's there. It's amazing. The world is an amazing place. Anyway, so subsident, we looked at the caves. Here's some amazing sinkholes. Subsidence over a large area, right? We talked about Venice. Mexico City, this is a cathedral that's not being used as an art house. And no, it wasn't built in this undulating way. Part of Mexico City is built on a wetland, and the wetland material sinks, compacts, and you end up with this differential settling. With subsidence, you're not really going to kill people unless you let a building get incredibly unsound and it collapses. But another structure in Italy, can you think of one that is off kilter? Anyone know what's going on there? Yeah, the Leaning Tower of Pisa, right? Did they build that to be leaning as a tourist attraction? Answer, anyone? No, right? It started leaning because it's also on wetland material. So what they did, the engineers looked at it and they said, oh God, it's going to collapse. And so they're trying to figure out, how do we get it to be a little still leaning so tourists come and see the leaning tower, but not leaning so much that we're afraid it's going to collapse. So you're trying to figure out, what can we do to engineer this? At first they were thinking they were going to put cables on the side that's leaning this way and pull it. And they realized that would cause the tower to collapse. So what they did, and then they thought, okay, we'll put sediment on the side that's leaning this way, beef it up. They said no. So what they did is they removed about 38 cubic meters from the raised side, and it was closed for 3 years as they did it. And so now it's no longer leaning to the extent that it was, and engineers have declared it stable for 300 more years. So feel free to go to the Leaning Tower of Pisa. So subsidence can be stopped, not reversed. So if you're doing solution mining of oil and gas, what you can do is, there's a lot of associated brine. You can inject the brine into the area where the oil and gas has come out of. You can't get the land to come back up, but what happens is the ground won't sink any further. And it's not the case, again, that subsidence kills lots of people. It's not a dangerous, deadly natural disaster unless buildings become unstable and ultimately collapse. But you can have infrastructure problems. There's a great picture, I don't think it's in your book, but of a fire hydrant in the San Joaquin Valley. And because of subsidence, they left the fire hydrant where it was, and it was about 25 feet off the ground because the whole ground lowered. So you can imagine that's not good for things like roads and bridges and houses, and a lot of coastal cities especially are built on wetland material, so that can happen. We don't have it as much in Boston because we put all these pilings through the Boston blue clay, but could happen if we didn't put the pilings on there. So, okay, we are at 7:06. That's the last slide. So I guess, Amelia, no sign of Eli, huh? So those who joined after, oh, Eli, you're here. No, she's here. I'm going to make Eli a presenter. Eli, can you hear me? Oh, you're typing wonderful. Hi. All right, I just made you a presenter, Eli. Can you possibly click on, because I couldn't get your PowerPoint slides, which are done as PDF. Oh, it's no problem. You're here now. Oops. So I have your video, but can you try to upload your PowerPoint directly on here? I don't know what that means. Maybe can you unmute your mic and get on the camera? So those who joined us after I started talking about this, Eli is in the Philippines where there's a tremendous number of landslides, and so she graciously, try it, Eli. So go up to the top, and it will say, I'll stop sharing. It will say, do you see share my screen? Or there's a little inverted triangle. Sorry to everyone, I wanted to do this before, but Eli couldn't get on. If you click on the inverted triangle, say share document, and it will upload your file. While you're doing that, let's see. Yeah, you're now a presenter. I put you in as presenter, and I don't want to waste people's time. So let's see. Can I play this with sound? Let me play your video first, maybe if you want to discuss this.
So we have storm surge starting to flood the ground floor of the hotel. Residents are evacuating up to the so we have storm surge starting to flood the ground floor of the hotel. Residents are evacuating up to the second floor.
Alright, sound check, anyone?
Any more in there, Josh?
Oh, perfect. Alright, so here is the video. First, apologies for the delay. I'm a little bit sick. Sorry for that, Professor Cole. So, I don't really look good on camera, for short. But my name is Eli, and this is a footage, real-life footage, of actually a couple of American volunteer workers. So they were taken aback by the storm. So you can see right now they're floating them on inflatable water beds. And to think that this is not actually the height of the storm, this was just the starting of it. So we could imagine, say, if we were already actually in the intensity of the eye itself. So this is when it was just starting to fuel up, which is around, as witnesses told me, around 3 a.m. and the very peak was around 8 a.m. This was in, Elisa, hello, this was in November 2013. I will explain more in my PowerPoint.
Eli, are you finding that you can upload the PowerPoint?
Yes, it's actually pasted in my Google Drive. Thank you, Professor Cole, for showing my video. Can you see it? The same link. It's the same link.
Oh, I know. I wrote you an email. I was trying to get you to upload it. I got an error message. So since you're a presenter, can you upload it from your computer? It might just want you to do the PowerPoint itself. I tried to do it. Let me try one more time. See, I have...
Sure, no problem. I was just thinking, though, if I would, could I give it to you in Keynote? Because if I think if I give it to you in PowerPoint, the formatting may be changed.
Yeah, sure. Try it. See, this is what I got when I tried to upload it. So, do you see it says share my screen? And then there's a little inverted triangle. If you click on the inverted triangle, go to share document, which is the second thing down.
Okay, share document. And
share document. And then, your PDF didn't seem to work for me. You might try it with that or try your Keynote. That's what I got.
All right. Oh. Okay.
Oh, wait. Is it going?
Hold on. I could not process it.
Hold on. Oh, it is. All right. All right. I'm sorry. You're gonna have to scroll down.
Okay. I think it's loading.
Yeah.
Quite slowly.
So sorry about this. So,
no problem.
Also, Elisa asked when this was.
Oh, Elisa, this happened November 2013, so I was a junior high student back then. So I was pretty younger. Yeah, pretty younger back then. I believe that if I could confirm on my end, classmates and dear professor.
Yes, absolutely, yes.
So I could see everything except for the title page. All right, no worries. Okay, please give me a moment as I bring out my... Okay. So I'll be dragging my screen and my Keynote speaker at the same time.
Yeah.
Is it okay? Oh, do you see two windows in the same screen? I'm sorry, Professor. It's just I'm not very familiar.
No, it's no problem. I'm so sorry that we didn't get to connect before class to do this. We just see, I'm going to have Amelia take over to help you because she knows more about this than you do, than I do. Sorry, than I do. So, Amelia, do you want to unmute and try to help out with this? Because Amelia had more recent training than I did, and I don't want there to be too many cooks. So, Amelia, maybe do you want to unmute your webcam and you can be the MC?
Right, here we go.
Hi, hello, Miss Amelia.
Hi, how are you? Can you hear me?
Doing fine, doing well. I wish I could open my camera, but I'm not feeling
Oh,
well.
no worries. I was just in that same boat.
I'm so photogenic. So Miss Amelia, do you see two windows being open, or do you just see because right now I'm sharing my screen. I'm kind of worried if you can see like my notes.
I actually cannot see your notes, so that's pretty good.
Okay. That's
the first slide.
So you can just see.
Oh yeah, you're scrolling. Yeah.
All right, perfect. All right, so may I be given permission to start, Professor Cole?
Oh yeah.
Yes, of course.
I think.
Yeah.
There she is.
Yeah. I'm just muting because I don't want there to be too many.
All right, perfect. All right, perfect. 7:15. So, good morning on my side. It's Friday, 7:15 a.m. in the Philippines. So a while ago it was 5 a.m. Yeah, so class starts 5 a.m. to 7:30 a.m. for me. My name is Eli Kushako, and I will be reporting on landslide and / storm surges. So I'll give you a brief info to the Philippines, which is my home country. I'd like to thank you all for the patience that everyone has showed, especially in setting up for the Zoom. So, the Philippines, everyone would seem to know it's an island, the biggest island, so the largest archipelago, which is 7,107 beach islands and counting. So, if you come to think about it, we have white sand, pink sand, black sand, yellow sand, all kinds of sand, all kinds of beaches. Right. So being a huge cluster of a beautiful group of islands can also have, its drawbacks. So we are also the most typhoon-prone country. We have an average of 20 typhoons every year, and 5 are destructive. Now, in the Southeast Asian side, we do not use the term tropical cyclones. We use the term typhoons. All right, so it could be cleared. Now, we're also seated in the specific ring of fire. Now, everyone knows that the physical location, and the geological location could make it pretty vulnerable to earthquake, volcanic eruptions. I believe that we've read the case study of Mayon in our readings and our notes. So that would be an example. All right, so going down. Now, here is a chart. Oops. Okay, what is happening? All right, sorry. So here is a chart of the frequency of the typhoon and landslides. May I ask if you could see my cursor or no?
What did you say? See what?
Only the computer. Oh, okay. The cursor?
No, so what you have to do is there's a little green arrow. So you click on the arrow. You see that? You can move that around. You see the arrow?
Green arrow. Okay, this one?
Oops, sorry, I'm clicking. Sorry.
Here? Wait.
I'm not touching anything again. I'm sorry, I'm ruining it.
Eli.
It's okay, Professor.
Do you see
this one? That one?
Sorry, do you see the upper
upper
bar that says the title of your file? So it's right underneath the Adobe Connect toolbar. Do you see that? At the very top of the window?
Is it on the upper right?
Exactly.
Corner?
It's not green yet, but there's a little diagonal arrow button. And if you click on that, exactly.
There you go. This one?
Yes. Perfect.
Finally.
You're welcome.
Thank you. So, thank you so much. All right. So there's as we all know, the Philippines is a frequency of typhoons. And a while ago, Professor Cole was actually discussing about the typhoons in the Leyte area. All right. So here, the red colors, as you can see from this area, mostly more on the Luzon area. Oops, okay, it's a bit difficulty using the cursor, but anyway, you can see it on the north side. That's the biggest island right there. It's almost full of reds, right? And actually everywhere is full of reds. And now the gray areas, so you can see the typhoon track. This is the most affected areas. So Tacloban, which is the small country, or rather the small island that was hit by Typhoon Haiyan, is actually in the heart of Manila, the Philippines. So it's a little bit lower than Manila. I cannot move my cursor. It's a bit weird, but I hope you can, somehow get the idea. All right, so okay, weird cursor, weird. All right, so so despite all of these disasters, we Filipinos are also known to be the most optimistic, resourceful, and happy people ever. So people have learned to live with this. We have, I think I've mentioned, I didn't mention it, we have 20 typhoons annually. That's annually. I mean, that's like the minimum. 20 typhoons every year, and 5 are actually category 3 and above. So that's how typhoon prone we are. But still, people find their ways to make light of it. Often you will see Filipinos smiling and having fun in the rain. One is even getting married, as you can see in the far corner. Okay, now back to our case study about Typhoon Yolanda. So the international name is Haiyan. So there may be some people that may be wondering, why is the name of the Yolanda is different, from the international name? So our local name is Yolanda. Now this is Elisa, you were asking about this. It happened on November 2013. And it affected 16 million people. Imagine, in one big island alone, it affected 16 million people. That's how much people it affected. And it's a category 5 storm. Okay, so it's one of the strongest storms. Now, how destructive it is, just look at the size. Can you see that the tropical cyclone, aka the hurricane, is as big as the Philippines itself? Yes, right. In fact, it covers everything from the tip down to the north to the west. It's like everything. So that's how destructive it was. Now it's even bigger. Yes, Professor Cole, thank you so much for your time. I hope you could also see the record. All right. And thank you, Miss Amelia, for recording. So it's even bigger than Katrina. So as you can see, that is Katrina. I'm a bit afraid to move the cursor, but anyway, that's a picture of Katrina, and it's a picture of Haiyan. So you can compare and contrast, the storms. It's also, although the eye is almost the same, the eye of the storm is almost the same, but rather the wind is quite stronger. So 195 miles per hour. It's the second largest storm and the most destructive typhoon in Philippine history. Now now regarding this documentary, so back when I was in junior high, I've actually watched the news helplessly from my couch, and I remember that I was actually crying because personally, my parents are born-again Christian missionaries. So it feels really helpless seeing your country, reported by so many nations suffering. And I knew at that moment that I was called to help, but I was in America, so what could I do? I couldn't make a difference. But that was when my thought was wrong. I could actually make a difference. So I fundraised by visiting a local high school, and I visit, with permission of the teacher and the faculty, I visit each classroom, and amazingly, every student and teacher gave $1 each, and the teachers gave $10 to $20. So I think in 12 classrooms and 15 teachers, it was a really huge school. I was able to raise $500 in a week. And so with that $500 a week, I promised them that I would make a small documentary, showing them how much of a difference their $1 made. So I was armed with my selfie stick, my Beat headphones with the mic, and my Samsung camera to document what really happened when I went home to the Philippines during the time. And it was already December, so it was Christmas. Now, in regards to Landslide, so there I am. So I was able to purchase a plane ticket together with my parents, my mom, and my dad. So it was just a 3-person job, honestly. It was really rushed, and also no one wanted to go there. Like, even if we had volunteers, most people would not want to go there because, number one, airplanes are limited, so the price of the ticket is really high, you know, because a lot of the airplanes was destroyed. And number three, there's still, it is said that the land still stinks. When I mean stink, it's stenches of human corpses. So not everyone would like to go there. But because I did the fundraising and I really wanted to show, you know, the students who helped and the teachers who helped what happened, so I decided to pursue. So from this plane window, you notice that there is this circular object. So at first glance, I was not aware, but if you look at it closely, it was actually landslides. Now, I believe that Professor Cole had shown a couple of pictures. So here is a picture I've taken from a newscaster. So this is it actually in zoom-in form. I actually was just passing through it, but I didn't notice. But this is it in picture form. Now, I just wanted to show you an experience. So these are not my images. These were taken from Google. But I actually had this experience in Baguio. So that's the mountain that I had a mission trip lately in. And it's funny because I actually emailed Professor Cole asking forgiveness because my lab was really late, you know, in submission. And I kind of explained that we are actually... we just recently got free of a landslide traffic, and she was asking, what do you mean landslide traffic? So I kind of explained, like, oh, it's like this. This is like my car over here, but my car was actually a mission bus. And there's huge piles of rock that it was blocking the roads bigger than these piles. So this is just a sample reference, and we couldn't move. And you see the roads, they look like worms, like, you know, like a really long squiggly type of worms that circles the mountain. So it took such a long time, 3 to 4 hours, for the government officials to clear the rocks. And sometimes you would even see tiny rocks, you know, falling from the ravine. So it was pretty, you know, pretty tense because you can never know when a rock is going to next hit you. But thank God we kind of survived. And that was like the wild story behind why I kind of submitted my labs really late. So Professor Cole, being the wonderful professor she is, she said, it's all right. And she actually asked me to present this for you guys and share my story. So up close, I would imagine not just landslides, but mudslides. So this happens when the silt in the soil has a lot of accumulation of runoff water. And this, if you notice here, there are houses here. They're actually not really that affected. So as you all know that the trees act as a barrier. So whoever planted their houses at these sides, they're very, very resourceful. But unfortunately for those who planted on these sides, well, they just run up into the water, literally and figuratively. Now, for Baguio is a city known for landslides and known for earthquakes. So what the government officials have, for what? Wrap up in couple. Sure, no problem, Miss Amelia. I'll speed it up. So there are strong foundations and safety measures. All right, I'll speed it up, guys, because I'm a little bit late. So back to the storm surge, Typhoon Haiyan. Oops. Okay. So basically, the people waited for the government to come with the supply. 10 days came and nothing happened. And it turns out there was actually some sort of political agenda that was happening. So for short, the government stopped the relief goods coming in because our president, former president, the Republican the Yellow Party, the Democratic Party, not the president now, he actually wanted the mayor to resign first because he was from a different political dynasty. And so as a result, I remember I've interviewed this government official. When you are starving, you will do things you never imagined you can do, and that is very much true. Now, I'm going to speed up, because we're a little bit behind time. So I've heard horror stories. When I went there, the first thing I did was actually interview everyone. So in this case, I interviewed local government officials, church officials, and sometimes even some random people. So mass bodies were piled up together with dogs, pigs, trash, animals. They were all together, mass graves. They started looting. If you can, to sum it up, it's actually like the scene of a Mad Max movie wherein people were just getting the beeline for their life. And and everyone was acting as they described as living zombies because they were so hungry. 10 days, no food, no water, no shelter. What do you think would happen, right? As he said, if you are hungry, you do things you never thought you would do. So the media also lied. They said 6,000 people, but it was 20,000 casualties actually. So it was really saddening during the time the government and the media, was trying to cover it up. So why they failed? Okay, I'll just it's mainly because of overconfidence and they didn't know what a storm surge was. So what was the lesson learned? The lesson learned is that first you have to set up and evacuate to evacuate properly. Third is that you have to take away the homes that are from the coastline and raise disaster awareness. Now I just want to share this last pic of for you. This is a person that his whole family actually died. His whole family died. His newly bought house was shattered down. And when they interviewed him and asked him about his faith, I asked these questions also to the people I interviewed, if your faith was shaken, kind of like in the Lisbon earthquake event. And all of them actually answered that, yes, it was shaken at first, but actually in the long run, if I will lose my faith in God, then who do I have left, right? Who do I hope for? Who do I pray to for tomorrow, right? In fact, this person right here, he mentioned that I shouldn't be alive, but I thank God I survived. That was his very question. Even when he lost 9 members of his family, his 2 houses, his farm, and everything. And because of that very highly optimistic quote, it ended up being the slogan in t-shirts, memorabilia. It was forever immortalized. So these are some of my favorite pictures that I've taken. I'm sorry I couldn't show everything all at once. Got just 15 minutes. Now, how $1 made a difference. So by God's grace, we gave appliances to families who want to start over. We gave help to some churches and to gifts to over 150 people. But this wouldn't be possible without those students sacrificing their $1 and without all those teachers giving a portion, of a small portion of what their salary could have been. So it's really amazing how people help. So I want to thank you guys for listening. I really, really want to share you everything, even all the horror stories, but unfortunately, we don't have time. So if you want to find out more details, please do check out my mini documentary link. Again, remember, I was back in high school, so it's not really professional, but if you really want to get the raw, unfiltered, uncensored cut of what really happened in that area and what, how the corruption caused people to have chaos, then please check it out. So thank you, and I hope you've enjoyed. Hope I'm not like rapping like a rapper, speaking so fast. And God bless. So thank you, Miss Amelia, if you could take over.
Hi, can everyone hear me? I think that is likely the case. So thank you so much. This was amazing, Eli. This is a lot more than I had realized had happened. I wouldn't be surprised if I spoke for more than myself when I said that. Wow, this is pretty astounding. I'm going to stop. Oh, yeah.
Thank you, everyone. Yeah,
sorry. I'm going to
sure.
stop recording right now.
Recording.
But I'll either Jen or I will check in with you about adding your materials if you are able to, willing to, adding your materials to Canvas in some form.
Sure. Would you like me to send you the link too? I've created a Google Drive folder. I could also attach, the link so you could maybe set up, not sure, maybe a thread or something. Yeah, you mentioned you wanted to set up a thread.
Yeah, like a discussion.
For people to. Yes, I would love that. Thank you. I just really wish to raise awareness of what is happening when politics can come into the play and how people could suffer. I just really thank God that we have a new president right now, President Rodrigo Duterte. So he's really clearing up the corruption nowadays. So, I mean, there will be a bigger social change than before. I want to thank everyone. I think I can see your comments. Thank you so much. Sam and Rochelle, Bonnie, all of you who commented, thank you. I would love to hear your comments and your thoughts. I just kind of want to warn you that my documentary could be morbid, very morbid and very raw at times. but I mean it's the truth, and the truth sets you free. So that's it. Thank you, Miss Amelia. Thank you so much.